It follows from the special theory of relativity that mass and energy are but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is put equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Kokra and Walton in 1932 experiments.
Si la nave de Bertrand estuviese adecuadamente equipada, podríamos ver ese misterioso efecto nosotros mismos. Este aparato es un reloj de luz. Dos espejos situados uno frente a otro, con una partícula de luz o fotón botando entre ellos. Cada bote es un tic del reloj, y en las manos adecuadas, un reloj así demuestra claramente que la velocidad cambia el tiempo.
Normalmente se producirían millones de botes por segundo, pero los hemos frenado para demostrar cómo funciona este reloj y cómo altera su movimiento el ritmo de los botes. Observarán que los botes son más lentos si lo muevo. ¿A qué se debe? Pues a que el fotón se mueve en zigzag para llegar a un espejo y luego al otro. Es un recorrido mayor que tiene que hacer el fotón, lo que significa que tarda más en recorrer ese trayecto, por lo que el reloj va más lento.
Aquí es donde colisionan la física y la ciencia ficción. Para el reloj en movimiento, el tiempo va más lento. Aunque si uno viaja con él como Bertrand, no se da cuenta del cambio porque todo lo que ocurre a bordo, incluido el ritmo del corazón y el funcionamiento del cerebro, se reduce en el mismo porcentaje. Cuanto más rápido viaja Bertrand, más tardará el fotón de bote en bote y más lento pasará el tiempo para él. Lo que para Bertrand puede ser una hora, puede ser un siglo para el resto de nosotros. De hecho, se adentraría 100 años en el futuro.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo a very strange transformation. They undergo an identity crisis. So let me show you what I mean by an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. These are very strange, very unfamiliar to us, but in fact, each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that moving around. It's really difficult for me to explain just why that is, but that's the way it is. Now, as you go to very low temperatures, the size of these packets gets longer and longer and longer. And then suddenly, if you get them cold enough, they start overlapping. And when they overlap, the system behaves not like individual particles, but particles which have lost their identity. They all think they're everywhere. This little wave packet over here can't tell whether it's this one or that one or that one or that one or that one or that. It's there and it's there and it's there. They're all in one great big quantum state. They're all overlapping. They're all doing the same thing. And what they're doing, to a good approximation, is they're simply sitting at rest. This Bose-Einstein condensate is very difficult to imagine or to visualize. I can imagine what it's like to be an atom running around gaily, freely, bouncing into things, sometimes going fast, sometimes going slow. But on the Bose condensate, I'm everywhere at once. I've lost my identity. I don't know who I am anymore. I'm at rest, and all the other atoms around at rest, but they're not other atoms around. We're all just one great big quantum system. There's nothing else like that in physics, and certainly not in human experience. So just to think about this causes me wonder and confusion.